This video is on electron configurations. I'm going to be doing them using the long form, and later you will use the short form in another video. So first, let's review what we learned in a previous video, and that's the different energy levels and the sublevels, and then the number of orbitals that go with them. So energy levels. In the first energy level, it is small enough that it only contains the S sublevel. And the S sublevel is small in that it only has one orbital. So there's only one space inside the S sublevel that can hold electrons. And one thing to note is when we talk about maximum number of electrons, that the maximum is that there's 2 electrons per orbital. So if there is one orbital, that can hold 2 electrons. So in 1s, we've got 2 electrons. In the second energy level, there can be an S sublevel and also a P sublevel. So in the S, there's still one orbital because it's S, doesn't matter if it's which energy level it's in, and that can hold 2 electrons. In the P sublevel, it's bigger though, and it has 3 orbitals. Think about that as like having 3 rooms. Remember, and in the last video, I talked about how one of them is on the x-axis, one is on the y-axis, and one is on the z. So they're all at perpendicular to each other. If I've got 3 orbitals, that's 2 electrons per orbital. That's a total of 6 electrons. So what about the third energy level? Well, the third energy level is bigger still, so it can hold electrons in the S sublevel, in the P sublevel, and it also has the D sublevel. So S holds 1 orbital, there are 2 electrons, P has 3, which is 6, and D has 5 orbitals, 2 electrons per orbital would be a maximum of 10. All right, so then our fourth energy level is bigger still. So here we've got S, we've got P, we've got D, and now here's where F starts. So S1 and 2 electrons, P 3 orbitals and 6 electrons, D 5 orbitals and 10 electrons. And F has 7 orbitals, which will then hold 14 electrons. All right, so we're going to put these in order, and we're going to talk about kind of this whole piece put together is called an electron configuration. So each electron in an atom is described by its, let's use correct grammar though. Its electron configuration. And the electron configuration is made up of what we call quantum numbers. And we're not going to go much more into quantum numbers, kind of what they are. But you should just know that that's what an electron configuration is. So the Pauli exclusion principle states that no 2 electrons in an atom can have the same four quantum numbers. That means that they cannot have the same electron configuration, like individually. And that also means, more importantly, it means they can't be in the same space. All right, so if we're going to write electron configurations, we have to put all these energy levels and their sublevels in order. And the order is what we call the Aufbau rule. So Aufbau means diagonal. So we're going to write diagonals that are going to put these in order from lowest energy level to highest. So lowest energy level is first. So first thing I'm going to do is I'm going to write all of these energy levels with their sublevels. So I'm just going to write them in rows. So in the first energy level, there is 1s. In the second energy level, there's 2s and there's 2b. It's p, sorry. In the third energy level, there's 3s, 3p, and 3d. In the fourth, it's 4s. Oops. It's 4s, 4p, 4d, and 4f. In the fifth, there's S, there's P, there's D, and there's F. So when I do these over here with the 4, you could replace them with 5, 6, and 7. I'm going to erase this so I have some space here. All right, so we've got 6s, 6p, 6d, 6f, and then 7s, 7p, 7d, and 7f. So the diagonal rule means we start up at this 1s, so here's where you start, and we draw a diagonal line. So the lowest energy is 1s. When you get to the end of your arrow, you go to the next line, which is going to be diagonal here. So after 1s comes 2s. Then comes 2p, then 3s. Then we've got 3p, then 4s, 3d, 4p, 5s. Notice how it's different than just if you went row by row left to right. Because after 3p, 4s is lower energy level than 3d because s is that much lower than d. So even though it's in the fourth energy level, the fourth orbit around the nucleus, it's still lower. It's easier for an electron to be in there versus a 3d. All right, so after 5s comes 4d, 5p, 6s. So you make sure you're drawing these in, and you're going to have to add, I think, in your notes some of this row if it's not there. Okay, then 4f, 5d, 6p, 7s, and then 5f. And these last ones, these from, let's see, I think it's, let's see, 7p. There's nothing after that. No elements have this many electrons at the very top end. But we'll write them in just because it kind of makes more sense. That's the possibility. Okay, so how does this relate to what we call an electron configuration? What is that? Okay, so here it is, a lot neater than how I wrote it. Let's do a few examples. So let's start with hydrogen. Okay, so when I look up hydrogen on, oops, I wanted to do this one. Okay, when I look up hydrogen on my periodic table, it has 1 electron. So I'm going to go back here. So I've got 1 electron. So my electron configuration is going to start here. And that 1 electron is in the first energy level. It's in that S sublevel. And I'm going to write a 1 here to say that I have 1 electron there. And that's the electron configuration in black. All right, so let's do another one. Let's do helium. Helium is the next element over. It's 2 electrons. So it's helpful to have your periodic table out to kind of look this up. So if there's 2 electrons, it's still going to start at the beginning with that 1s. And S, remember, can hold 2 electrons maximum. And if it only has 2, that's where they go. So there's the electron configuration for helium. So now let's do a bigger one. Let's do something like chlorine. And chlorine has 17 electrons. So I'm going to, again, start at 1s. There's 2 of the 17. After 1s, I follow this down, comes 2s. Notice there's no comma, there's no space. It's just like it's one word. And s can hold 2 electrons. So there's 4 total. 2 plus 2 is 4. After 2s comes 2p. And p can hold 6 electrons maximum. So I'm going to put a 6 here. So there's 10 of my 17 electrons. After 2p comes 3s. S can hold 2. So I'm at 12. After 3s comes 3p. And it's a p, so it can hold 6, just like 2p, but I only need 5 more to get to 17. So all of these superscripts, these numbers up here, have to add up to your total number of electrons. And so if I said, what's the electron configuration for chlorine, you would say, you would write this, and the way it would be said would be 1s2, 2s2, 2p6, 3s2, 3p5. We don't say squared or anything like that. All right, so let's do a little bit bigger. Let's do iron. And I'm going to leave some space here because I'm going to come back to chlorine in a minute. All right, iron has 26 electrons. So we start at the beginning, 1s2, 2s2, 2p6, there's 10. Then 3s2, 3p6, remember p can hold 6. So now I'm at 18. So after 3p comes 4s, careful and follow the diagonals. S holds 2, so 4s2. So now I'm at 20. So I get to go 26, so after 4s comes 3d. So 3d6 is my 26. All right, so now what about if I have something like chlorine with a -1 charge? So I have the ion. Remember what a -1 charge means. It means you have one more electron. So this would be 18 electrons. So all that's going to change in my configuration is I'm going to add one more. So it's still going to be 1s2, 2s2, 2p6, 3s2. Then it's going to be 3p6 for 18, which will be the same configuration as argon, because that has 18 electrons. All right, so how about iron? What if we take iron and we figure out the electron configuration for one of its ions? Iron can be +2. So now when it's +2, that means we lost some electrons, in this case, 2. So we still have 26 protons, but we'd have 24 electrons. So this configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. 2 fewer. All right, I'm going to do one more. We're going to do a nice long one to kind of get a whole bunch and write all this out. All right, so I'm going to write it over here. So we're going to do Ta, which is atomic number 73. So 73 electrons. All right, 73. Okay, so I'm going to write 1s2. We always start there. 2s2, 2p6. So we've got 10 so far. 3s2. After 3s2, if I come back up here, right, comes 3p6. Then after that comes 4s2. Then 3d10. So at this point, if I add them all up, I'm at 30. After 3d comes 4p. 4p6, right? P can hold 6. After 4p comes 5s2. I'm at 38. After 5s comes 4d. D can hold 10. Then 5p6. Then 6s2. All right, after 6s2, I've got 56. All right, so I'm not there yet. After 6s, if I look at my chart, comes 4f. Now F, if I go back to here, F has 7 orbitals, so it can hold 14 electrons. So let's see, I said I had 56 plus 14 gives me 70, and I got to get to 73. So after 4F comes 5D, and I need 3 more, so it's 5D3. So these are electron configurations long form. It's always lowest to highest energy level, and you're using this Aufbau diagonal rule to find the pattern of lowest to highest.